Hello, everyone, and welcome to our second lesson in Unit 2, where we're looking at the change in exponential functions. We have two learning targets in this lesson, and there's actually several examples that we're going to go through to really look at this concept in lots of different ways. If it seems a little overwhelming at first, please ease into it and focus on the classwork, because I think the classwork helps to clarify the true goal of this unit. We're looking at lots of examples just to look at this from various perspectives, but if you really do want to cut through to the actual true goal and meaning of this lesson, I think the classwork is a good measure of that. So I just wanted to get that that message out of the way first, and let's dive into a couple of examples. Imagine two fast-growing vines that sprouted from Jack's magic beans. When you begin measuring the vines, they're both 10 feet long. For the next 4 days, vine A's length increases 50 supposed to be feet, I apologize, each day, while vine's B length doubles each day. We're going to be defining a function to model the length of each vine since it was 10 feet long. So we're going to start with vine A, and we're going to model this scenario using a table first, and that's going to be what we base an equation off of. So before we even begin, before any time has passed, the vine is 10 feet long, and then it's going to go up 50 feet each day. So every time day goes up by 1, length is going to go up by 50, so that's going to be 60, 110, 160, and 210. Now, I hope you can see that we can think of it as every day the vine becomes 50 feet longer. Well, there's a pattern there, which is if 2 days are passing, then the vine is going to become 50 feet longer twice, or 50 times 2. If 3 days pass, the vine is going to be 50 times 3. And if t days pass, the vine is going to become 50 times t feet longer. Now, that's going to be on top of the original 10 feet. So we can write an equation for its length by taking 10 and adding 50 times whatever number of days has passed. So if 5 days have passed, it's going to be 50 times 5, but then it was already 10 feet to begin with, so we add that and we can find the length, and we now have a linear equation that can match this arithmetic sequence. Let's jump over to B, where we're doubling the length each time. So every time the day goes up by 1, the length is going to double. So 10, 20, 40, 80, 160. Every day, the vine is going to become 2 times as long. So we can say if 2 days pass, the vine is going to become 2 times as long twice, or 2 squared, 4 times as long. If 3 days pass, that's going to be 2, 2, 2, or 2 to the third feet long, or 8 times. And once again, we can generalize this by saying 2 to the t after t days have passed. If we start with 10 and multiply again and again by 2, we're going to start with 10 and going to multiply 2 however many times the days have passed. So if 5 days have passed, it's going to be 5 2's. So 10 times 2, 5 times. We can represent that with 10 times 2 to the 5th power. Once again, an equation to represent the length. This is an exponential equation that represents this geometric sequence. All right, let's go on to our second example. Which vine, will be longer 3 days after the day that they were each 10 feet long? What about 30 days after? Well, we can use our equation that we've developed and just plug in 3 for the amount of time. 10 plus 50 times 3 means it's going to be 160 feet long. And 30 days after, 10 plus 50 times 30 means it's going to be 1,510 feet long. Vine A, that is. We have vine B. We have an equation to represent that. If I plug in a 3, we can see that it's going to be 80 feet long on the third day. This is supposed to be a 3 and a 3. I apologize. 30 days later, we're going to take 10 and multiply 2 30 times. It's going to be about 10 billion feet long. So after 3 days, vine A is actually going to be about 120 feet longer. But after 30 days, vine B will be about 8.5 times as long as the distance from Earth to the moon. This is very, 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 very long. That is a tremendous distance. Now, I hope you can start to realize a pattern there. It would seem as though a geometric function is going to increase much more rapidly than an arithmetic one. And if we look at a graph of these, we see that that is in fact the case. An arithmetic function is just linear. It's just going to keep going at the same pace, whereas a geometric one might start out slow, but it is going to build and build and build and build and really take off. If we examine these graphs on the same axis, we see that for all values of t that are greater than about 4.5, vine B is going to be much longer than vine A. And also, we can look at an example to see that that is in fact the case. What if we were to slow down vine B? Rather than doubling, we're going to only increase it a little bit each day, about 5%. So not a tremendous amount, but it's still a little bit. And it's still going to represent a geometric or exponential sequence, an exponential function, that is. So vine B isn't doubling anymore. It's only going to be growing by 5% each day. So if vine B is growing by 5% each day, it's going to have a growth factor of 1.05. And the reason it's going to have a growth factor of 1.05 is because it's going to keep 100% of its length. And then on top of that, it's taking 5% more. It's growing 5% more, which gives us 105. That represented as a decimal is going to be 1.05. So our equation for B, rather than 10 times 2 to the t, it's only going to be 1.05 here. So it's much, much, much less rapid than when there was a 2 there. But let's see what effect that has. After 180 days, let's kind of go far out into the future, about half of a year. Vine A is going to only be about 9,000 feet. And even though we've slowed vine B down tremendously, vine B is still going to be much more than vine A. It's not growing as rapidly, but it's still going to take off and be much, much, much longer than vine A, which is going to be 65,174. So it's going to be about 56,000 feet longer than vine A. So yes, we see once again in the graph, we saw that the geometric sequence took off much more rapidly than in a linear. And here, even though we slowed down the geometric sequence, it's still increasing more rapidly and overtaking the arithmetic function. So essentially, linear functions, because they have a constant rate of change, and exponential functions, because they have a constant percent change, the exponential function will always eventually outpace linear functions. In fact, it's going to outpace almost any other polynomial that we can think of. Exponentials are really going to take off and be the most drastically increasing functions that we're going to be working with. Now, equal changes in the independent variable, the exponential function, are going to create consistent percent changes in the dependent variable. That's an important thing that I really want to get to the heart at. That's the true heart of our lesson today. Before, when we looked at tables, let's think back to when we looked at linear and quadratic tables, we would look at the rate of change and we'd see patterns in there. Well, that's all we're doing here, except instead of comparing linear and quadratic, we now have linear compared to exponential. So linear, you're going to see constant rate of changes, just like in the first unit. And when we're dealing with exponentials, you're going to see constant percent changes. So you're going to be multiplying by the same thing each and every time. That's the key idea here. Let's become a little bit more familiar with these equations, though, because you're going to be seeing a lot of them, and it might kind of be useful to know what each of these pieces represent. So when I say things like growth factor, et cetera, it will hopefully make more sense, and you know kind of where I'm pointed and where I'm looking at. So if I were to have an exponential equation like this that describes a rocket's distance above the ground, I could say that its initial height, was 15 feet off the ground, and this distance is quadrupling, or going 4 times as high each and every time the value of t increases by 1. Now, quadrupling, we could also think about it as an increase of 300%. Why can we think about it as an increase of 300%? Because if I only increase by 100%, that's not actually an increase. I'm just keeping the same value. If I keep 100% of my money, I'm just keeping my money. I'm not going up, I'm not going down. So if my money's going 4 times as large, that's actually going to be an increase of 100 plus 300%, or 400 total percent. So we can think about it as an increase of 300, but technically I'm getting 400% of whatever I started with. Here I have an initial height of 5, and the distance is increasing by about 30%, or a growth factor of 1.3 every second. Here I have an initial height of 12 and a growth factor of 1.07, or we can think about that as an increase of about 7% every second. Example 5. Another rocket is 30 feet off the ground when it lifts from the launching site. Its distance from the ground, g of t, doubles every 3 seconds. So here we're actually going to notice that we're jumping a little bit. I'm not doubling every second. I'm doubling every 3 seconds. So I actually have to go 1, 2, 3 spaces to get double the height. This is going to be a challenge if I want to, let's just say, estimate something into the future. I have to go at full 3 seconds before I see double the behavior each time. Well, if that's the case, and if I wanted to represent the scenario with an equation, I can think to myself, all right, if every 3 seconds the rocket's distance from the ground doubles, well, in order to write an equation, I need to know what the 1 unit growth factor is. I need to know how much I'm going up each single time, not every third time. So what I can do is, all right, if I'm taking 30, multiplying by b, or in other words, if b times b times b is the same thing as multiplying by 2, I can take the cube root of both sides, and I see that I'm actually increasing by the third root of 2 times the third root of 2 times the third root of 2 times the third root of 2 will be the same thing as multiplying by 2 every third time. So if we started with 30, I can write an equation that has a 30 here. I found my b value, which is my growth rate right there, and then I have some measure of time right there, and I now have an equation that represents this scenario. Let's do something similar, except I'm not told if it's a linear and exponential situation. So here I'm told that the water levels in the western United States are dropping. If the recorded water level of a lake in this region was 1,215 feet in 2015 and 1,042 feet in 2020, what methods might we use to project what the water level will be in 2035? So here I'm trying to take data that I know and project into the future, but I'm not told if this is increasing linearly or exponentially. So we're going to do both. We're going to take this scenario and represent it with a linear equation and then make an estimate. And then we're going to represent it with an exponential equation and make an estimate. So once again, I can model anything with a table if I'm given some data values. So I'm going to say my initial value at year 0 is 1,215 feet. And then I have to go 5 years out to get to 1,042. But I don't know how much I'm going up each time. But because this is linear, I know that if I take this value and add 5 somethings, I'm going to get to 1,042. I'm choosing to represent those somethings with the letter m. Why? Because we're dealing with a linear function, and rate of change is often represented with m, because ideally rate of change is the same thing as slope, and we've been using the letter m to represent slope for the longest time. So I'm going to do that here. My initial value plus 5 somethings, my rate of change or my slopes, is going to have to equal what I end up with. So I can do some arithmetic, subtracting 1,215 from both sides and then dividing by 5 to see that I have to go down by about 34, 35 feet each year to get to this lower value 5 years from now. What about in an exponential situation? Well, here I start with 1,215 and I have to multiply something 5 times to get to 1052. So if I have 1042. If I have 1,215 and I'm multiplying by something 5 times, I can divide both sides by 1,215. That gives me an approximate value, but then that's equal to b to the 5th. So I'm going to have to take the 5th root of both sides. And that gives me it's a growth factor technically of 0.97. The reason I say it's a growth factor technically is if you notice this value is less than 1, and if we have a value less than 1, that means I'm losing something. I'm not keeping 100% of what I have. I'm only keeping 97% of what I have. If I'm only keeping 97%, I'm actually going down each and every time, which makes sense considering our scenario is actually decreasing in a water level. So now that I have an equation, 1,215 minus 35 feet each time, and 1,000 215 times 97% each time, I can just plug in 20, which is 20 years from now is going to be 2035, at least when we started this problem in 2015. And that gives me an estimate if we're using a linear model of about 523 feet. If I'm using an exponential model, it'll be about 660 feet. Now, ideally in the real world, we would kind of know which is the best model, but the whole point of this example is to show you how we can take data and represent it with either a linear or exponential, sort of to go through the process of how you would do it with one or the other, regardless of how it actually is behaving. If we were told how it's behaving, we would then, of course, choose whichever method is the best. All right, I hope this video was helpful. I know that is a lot all at once, so please feel free to pause, rewind, all that other stuff, and also think of the classwork more as a guide of what the true meaning of this lesson is. This lesson here is really just meant to walk you through several different ways to think about the concepts of comparing a linear and exponential function with tables and equations, and then how to look at exponential equations and sort of understand the different pieces and how they're used and all that other stuff. So please let me know if you have any questions or concerns, and I look forward to working with you in class. Take care, everyone.